I thought we just quickly recall these interpolation schemes that we had so far. In part one, that's where we stopped, basically. We stopped with these phase interpolation schemes, the upwinding scheme, linear upwinding scheme, and central differencing schemes. And the main point here was we wanted to have like the finite volume approximation for this expression. So we had this volume integral over the cell of a quantity where we have u is our field, for example, the temperature field could be, dotted with the normal of the phase, and then integrate over the phase. And this is going to be approximated with a finite volume method using the expression on the right-hand side. And there you see we have these values of u at the phase centroids, which we don't have. So we need to interpolate these values somehow. And for that, we can choose these different schemes. It's like infinite differences where you have forward scheme, backward scheme, central schemes. The same is applied here with these different finite volume schemes that we have. For example, the upwinding scheme, linear upwinding, central differencing. They all try and interpolate these values of u at the phase centroids. And then I was just giving you the formula for these different schemes as well. So for example, if you have an upwinding scheme, then you would either take it from the cell, your reference cell, or you take the value from the neighboring cell. And the way you decide is by the flux that you would look at. So these schemes are mostly applied when we would have, for example, a convection where we have a transport, which is described by a velocity vector. And then if the transport goes in one direction, we would decide if it's the flux positive or negative. Then we decide from which side we are taking the value. That would be the upwinding scheme. So the idea behind these schemes is coming from advection problems, where we have a quantity that gets advected by convection, and then we have these fluxes going in a certain direction and then decide which value we would take. Same for this linear upwinding scheme, where we would also decide from which side we would take it. So here again, we would have, like, depending on the flux, if it's positive, we take it from our reference cell, and then basically include the information from the gradient of the field. We not just take the centroid value at the centroid P, but we add a linear interpolation, given we know what the gradient is in that cell. And if the flux is negative, we take it from the neighbor. So we interpolate then from the neighbor, centroid N, and again use this linear interpolation, given we know what the gradient would be in that cell. And D here, that would be the distance between the phase centroid and the cell centroid. So it's a linear interpolation. But the point here with linear upwinding scheme is you kind of only use your local information from one cell. You don't need a neighboring cell information at this point. But you need to figure out what the gradient would be, for example. And then central differencing is using like a linear interpolation between your neighbor point and your cell. centroid point. So if you have a cell here, we have the centroid point P at location XP, and then we look at a different cell which has centroid N with a position Xn. And then for us, it would be finding the value at the centroid of the face, the common face between them, so at X alpha. So this is then a linear interpolation between these. Now in 1D and in structured grids, this is fairly simple. But as soon as we have unstructured grids, then if we connect, let's say we have two cells, and if we just connect the centroid points and use a linear interpolation between them, then we're doing an error because we're not interpolating to the actual face centroid. So there is a difference, a correction factor here. How do I plot that? But you see this difference here. We would need to correct that if we have these unstructured and distorted meshes. So it becomes a bit more complicated once we want to have a better accuracy for distorted meshes, for example. If it's a structured grid, which means we don't have this distortion, then this interpolation is fine, because then we are actually going through the face centroid as well. And for us, the problem is 1D, so we don't have that issue. So just be aware that these schemes, sometimes they would need further corrections to it. Good, let me get rid of that. Now the schemes here, they try and interpolate what the value of U is at the face centroid. What we still need is a gradient scheme as well, where we need to figure out what the gradient of U is at the face centroid. So this is actually the scheme that we're going to use for our Poisson's equation, a diffusion equation. So let me put that down here. This is now the new part where we need to have some sort of a gradient calculation. And so the idea here is we have two cells. We have a value, let's say UP, and a value UN in the neighboring cell. So this comes from the centroid P, this comes from the centroid N. And what we are interested in is the gradient at the face alpha. So what we actually want to know is what is the gradient of U for the centroid alpha. So again, we can use a central difference approach for that. So Yeah, let me put that down. The central difference approach. I would have the gradient of u at position of the phase centroid x alpha is then just the difference un minus up divided by the distance of these centroids. So this gives us the gradient value at the phase center position. Again, this would need corrections if the cells are distorted and we have an unstructured mesh. Again, there will be corrections to that formula to make it more accurate. So let me just put that down. So we can call these meshes either non-orthogonal or there is also skewed meshes. The elements are skewed. It's not quite the same, non-orthogonal and skewed. But in both cases, corrections can be applied to that formula to make it more accurate.
Professor?
Yeah?
I noticed that only in the linear upwinding scheme that we should use the gradient, right?
So,
in the
right, so let's look at the linear upwinding scheme. There we do have, for example, these gradient terms, up and un. So those would be, so the gradient calculation, the idea here is we have the divergence of a gradient of u. And with the finite volume approach, we then basically express this as the integral over the surface and then have expressions like that. So you see now the interpolation is using grad of u, position of the face centroid position times n, the normal of that. So see here we would need the gradient of u, whereas on top here we just need u, the interpolation of u. So upwinding, linear upwinding and linear or central differencing, they try and find this u value at the face. And the linear upwinding scheme takes advantage of knowing within the cell what u of p is, but also what the gradient is at the centroid. So plus the gradient of u at p, and then we can linearly interpolate the value so we know what then u alpha is. Here is a slightly different for the gradient. So we want to know what the gradient value would be at the face. And the simplest approach is this central difference approach. Similar to this central differencing above for u. Here we just figure out what the gradient would be, taking the neighboring value into account. This is the most simple scheme. So, but for linear upwinding, you see, for example, this gradient gradients are needed at the centroid, cell centroid P and N. And one way to do it is using again, a Gauss approach. So it's sometimes called P. So what about having this for, let's say, for this linear upwinding scheme? So the sometimes called green or Gauss approach for the gradient would look like that. So in 3D, we use Gauss theorem again. And then the gradient at the centroid point becomes this expression with 1 over the volume times the sum of the U alpha times NE alpha times the phase area. So it's pretty much what we had above, but now this is the interpolation for the gradient at P. So if you remember, we had this for, that's also the approach that we had in the paper from Dolmy and Tarantula. I can try and approach this gradient if U is smooth. So what does it mean? Basically, it means that for a cell, in order to find the gradient at its cell centroid position P, we just need to know what the values of U are at its phase centroids. So if we know what U alphas are, we can interpolate the gradient within that cell. But now what are the values at the cell, at the phase centroids? Again, then it comes to this problem. We could interpolate these values, for example, using these schemes. Sometimes what is done is one tries to interpolate what these corner points are of the cell. And then once we have these two corner points, we can calculate what the centroid value would be. And once we have the centroid values, we could calculate what the gradient within that cell should be. So there is like a bunch of steps in order to get to it. So the schemes to calculate these phase centroid values, one could use linear interpolation. And there is also the nodal, that's the one with the corner points. Nodal average, for example, or averaging called, in order to get to these. A slightly different approach, which doesn't need this Gauss approach, is using a least square solution, finding the least square solution for the gradient. So there are a bunch of different schemes actually, which are proposed to obtain, for example, what these gradients would be. In our 1D world, this is much simpler. We can't just for now use this central difference approach. Now we have the gradient at the face. And then find the expressions that we need. So you see in the finite volume method, there's quite a variety of schemes that you can apply, and it depends very much on your problem, which scheme you would want to apply. Some schemes like the upwinding scheme is more stable, other schemes are more accurate, but they might have these fluctuations and oscillations. So then you play around with different approaches. The same with the gradients. Again, there's a bunch of different schemes you can try out to get these gradients. So let's look at how to discretize now our equation, how to discretize the Poisson equation with this finite volume scheme. So what we start with first is, let's discretize the domain, our physical domain. Omega. Into a mesh with grid cells omega E. So then the domain omega becomes the union over all these grid cells. So in the finite volume method, usually it's referred to as grid cells, these elements. Whereas in a finite element method, you would refer to them as finite elements. But in a finite volume world, you rather speak about cells rather than elements. But we keep interchanging that. So what about the integral form? Well, let's look at that. The integral form for our equation becomes now the following. We have the diffusion term, the second order derivative of u with respect to position x, plus our fourth term dx. So this would be the diffusion term. And this would be our fourth term. Now it becomes just the sum over all these grid cells over the integral of the grid cell u dx, and the same for the force. Dx equals to 0. That was the equation. Let me see if I can move that a bit. So that means we now look at each grid cell, what this integral value is, and we try and approximate these integral values for each grid cell. So let's start with the fourth term. That's the most, yeah, probably the simpler term. So the fourth term, so let's look at grid cell omega E. And again, like, let's make the problem simple and assume that we have a piecewise linear fourth term f of x. What do we find? Well, we can have the integral over e of f of x dx becomes, so if f of x is piecewise linear, it means we have the value at the centroid p plus this linear term, the grad of f at p, times the integral of the distances x minus the centroid position xp dx. So we just use the definition of a piecewise linear function f. And then you see again here this integral for the centroid vanishes. That means all we're left with is the value at the centroid fp times the volume of that grid cell. And if we recall from last time, the centroid position is also equal to the average within that grid cell. So it would be the average of f times the volume. And again, this would be second order accurate in case our function is not piecewise linear but has nonlinear terms. Then this approximation at least would be second order accurate. So often when you look at the finite volume approach method, you see that people use the cell averages of the quantities, which if we use this cell-centered approach becomes the same like using the value at the centroid position. So Fe, this would be the volume of our grid cell omega E. Fp, that's the value of f at the centroid position xp. And f with a bar on top, that would be the cell average of the function. But so very simple, already we have now the expression that we're looking for the fourth term. Fourth term just becomes the centroid value times the volume of the cell. Now let's look at the diffusion term. And here we start with a more general case in 3D. So the diffusion term can be rewritten using Gauss theorem. So what we would have is the integral with the divergence of the grad of u. That would be the diffusion term in 3D. Now you see with Gauss theorem, this becomes now the integral over the surface of the grid using the gradient of u times the normal at the surface integrated over each surface, which becomes for each surface alpha the integral over just that alpha surface of grad u dotted with the normal of that surface times ds. And now these integrals over the face alpha would be approximated now just by the value at the face centroids. So then we have S alpha, N alpha times the gradient of u at the centroid of the face. That would be the general case, how we would approximate these terms. So here S alpha, that's the surface area. Of the face alpha. The grad of u alpha, that would be the gradient at the face centroid, x alpha. And then n would be the normal to that face. So if you think of that grid element, so there would be xp, then we would have here all these faces alpha. Each face has its associated normal vector n alpha, which points outwards. So then the diffusion term will be approximated by the sum over these expressions for each phase. So in 1D we can simplify this a little bit. So you see our integral term looks like that in 1D. And so if U is smooth enough within the grid cell, we can just write this as the grad of U from the endpoints of that cell, which I call XA. So think of having a cell in 1D that goes from xa to xa plus 1. We have the centroid point in the middle, xp. And here we do have like the value of up. So this is just written out, grad of u at position xa plus 1 minus the grad of u derivative at xa. So how do we find these gradients? Well, we use the gradient scheme. If we know what the neighbors are. So let's assume we have a neighbor point, let's call it xp plus 1, and a neighbor centroid point xp minus 1. They have their associated values, up minus 1, and this one has value up plus 1. So we use this central difference approach. So we interpolate the value here to find what the gradient of u would be at position xa plus 1, and the same on the left hand side. Here we want to know what the grad of u is at position xa. So we approximate these derivatives using this central difference scheme. We can call this up plus 1 minus up divided by these distances between the centroid points. Minus the same on the left hand side, up minus up minus 1 divided by these differences. Maybe we can shorten the notation a bit by assuming that here, for example, the distance, we call it the distance delta plus between the centroids, and here a delta minus. Then we can just write this as 1 over delta plus of up plus 1 then 1 over delta minus up minus 1 minus 1 over delta plus 1 over delta minus up. So this would be our discretized scheme, basically, for the diffusion term in 1D. Taking these neighboring centroids into account. Is that clear so far, what we're doing? So now we have a discretized scheme. You see we have the force term on top, discretized. We have the diffusion term, now discretized. So what we can think of, what we are aiming for is like a matrix form, where we would have a matrix, let's say K times our unknowns, degree of freedom is D vector, is equal to the right-hand side F. And if we look at these expressions, we see that we would have something like a term where we have 1 over delta minus. Next element would have UP factors, and then an element entry with delta plus. Times the vector which has these UP minus 1, UP, UP plus 1, etc. So this would be K, our stiffness matrix, times D, the vector with the unknowns, equal to F, etc. So then we can put it into this matrix form. That would be the idea. Clear so far? Good. So what we still need to do are the boundary terms. So let's quickly look at how these boundary conditions would look like with a finite volume approach. So the boundary conditions for our problem, we had both Dirichlet and Newman conditions. Maybe let's start with the Newman boundary. It's a bit more simple and more direct to consider. So the Newman boundary we had on the left side. So this is our boundary condition at the left boundary. So let's look at that cell where we had the very first cell, basically, the left boundary. Let's call it x0 and x1. And then we would have a neighboring cell at xp plus 1. See, we don't have the neighbor on the left anymore, because this is our boundary. So how do we approximate now our integral or diffusion term for that cell? Again, in this case, that would be the grad of u evaluated at x0 and x1. Which is this evaluated at x1 minus this gradient evaluated at x0, which is 0, position 0. Now you see we can just use the Newman boundary condition here for that derivative. Can just directly use this minus h for that. But the derivative at x1, we still use this central differencing approach. So here we would need this neighboring cell in order to find the derivative of u at x1. So we can do that. We can use, for example, again, the distance delta plus. So then we have a term 1 over delta plus of the centroid value at up plus 1 minus 1 over delta plus value at up. Then minus h, so plus h. So just to be very explicit, for this cell element, shall we call it our omega 1 cell? What we are looking for are these expressions for the diffusion term plus the force term equal to 0. So then the diffusion term here, we have this 1 over delta plus up plus 1 minus 1 over delta plus up plus h. And the force term is just the value fp equal to 0. So think of our matrix form. We would have a matrix form that looks something like that. 1 minus delta plus and 1 over delta plus positive and then 0. Times the degrees of freedom. So we would have up plus 1, etc. Equal to the right-hand side. The right-hand side would be Fp. Now realize there is the volume missing. So if we bring this on the opposite side, we have Fp V1 minus h for this very first cell. Is that clear? Clear how we will put this into a matrix form? So see, the Newman boundary is fairly easy. We can actually not just, we don't need to interpolate this value anymore. We can just stick in the boundary condition for this value. It comes from the Newman boundary. Unfortunately, that's not the case anymore when we look now at the Dirichlet boundary. So let's see how the Dirichlet boundary would look like. Here our boundary condition is on the right side, so u at 1 would be equal to q at the right boundary. So what happens with our stiffness term? We have this very last cell. Let's call it Pn, the last nodal point xn, xn minus 1. And then the neighboring cell would have xpn minus 1 as a centroid. So for our last cell element, so let's call it omega n. We have this diffusion term that we need to approximate somehow, which is this derivatives at the position xn minus the derivative at position xn minus 1. So the question here is now, what is this derivative at the boundary point xn? When we have no information from a neighbor. Pn plus 1. So for the term here at xn minus 1, we can use again the central differencing approach to get the derivative at point xn minus 1. But now we need to have the derivative at position xn. For a Dirichlet boundary condition. And this is something we have to interpolate as well. And the most simple way that we can do is, what we know is u at this point, the boundary point. So how do we get this derivative? Well, we can use a backward differencing scheme. So we just interpolate the derivative between xn and the centroid position. And this would be a backward difference or backward difference scheme. remember from finite differencing. So the derivative at xn now is just this approximation of u at xn minus u at xp divided by the distance between n and p. So here we can call this the delta plus 1/2 So this would be 1 over delta plus 1/2 of the value at xn, which is q now, from the boundary condition, minus then the value at the centroid position at p. So now we have the derivative approximated using the boundary condition value. So if you remember, what's the order of that scheme, finite difference scheme, the backward difference scheme? Is it first or second order accurate?
First.
Only first order accurate, yes. Which is not ideal. In principle, we would like to have at least a second order accurate scheme. Because then also the other schemes are at least second order. So this is really just a very simple, maybe the first approach in order to use a Dirichlet boundary condition for that diffusion term. How would you achieve a higher order boundary term? What would you do to do that?
The question, please.
So you see, when we use this first order approximation of the derivative, our kind of finite difference stencil involves the value at xn and the value at xp. So with these two values, we end up with a first order approximation of the derivative. How would you achieve now a second order accurate approximation? Well, you would use more points. You would use a larger stencil.
And minus
So
1.
which points are available? Well, we could use this one from the next centroid. So one way to do that is you would use the Taylor series for these points. So just to outline this, approximations. So you would look at the Taylor series approach. And you would write the Taylor series for the position at Pn, UPn. We can write this as a Taylor series around Xn minus this delta X, basically. This delta 1 plus 1/2, we called it. So then the Taylor series is U at Xn minus this delta plus 1/2 times the derivative of U at Xn plus 1/2. Now the second order terms is delta squared times the second order derivative of U at Xn plus additional terms, etc. Good. Now we can do the same for the centroid point at Xn minus 1 and evaluate what the Taylor series would be around Xn minus this delta, whatever we want to call it. This could be plus 3/2, for example. So then we have U at Xn minus delta at 3/2 times the derivative of U at Xn plus 1/2 this delta squared and the second order derivative of U at Xn, etc. The additional terms. So now it's basically a question of adding these two Taylor series together such that we find the derivative expression for grad U at Xn. So you would try and cancel out the second order term. And then basically have something that has a value at UXN with a factor A plus a factor B times UPN plus a factor C times the value at Pn minus 1. And the rest would be then a truncation error that goes with the third order derivative of U, which means we would have at least second order accuracy. So the question then just becomes basically what is these factors A, B, C? Because this is given by the Dirichlet boundary. And A, B, C, these would just be the factors for the second order scheme. I'm not going to write these out now, but you see how you would construct the second order boundary expression, for example. Good. For now, we'll just use this simple approach, the first order boundary approach, with this backward difference for now. So then what do we find for cell element for the very last one? So omega n. We have the diffusion term, dx, plus the force term. So this diffusion term, we had it above. So let's u at xn minus the grad u at xn minus 1. Plus here the force term, Fn times the volume equal to 0. And so this very first derivative here at xn, we approximate now with this backward difference scheme. So then we had this 1 over delta plus 1/2 q minus 1/2 up. And then the other derivative is just the usual derivative with the neighbor cell. Oops. So minus, now we had 1 over, let's call it delta minus up minus 1 over delta minus upn minus 1. Or maybe upn. And then, yeah, let's bring over the force term. It's minus Fn Vn. And so let's again think of the matrix form. Then we would have for, let's say, upn minus 1, we would have a term plus 1 over delta minus upn minus 1 minus the 1 over delta plus 1/2 plus 1 over delta minus up equal to the force term, and then have this boundary term brought over to the right hand side. So if you think of the matrix form like in this case here, so the stiffness term, we would have the very last point is upn, and then the second last n minus 1, etc. equal to the fourth term here, we would have Fn Vn minus this delta factor times Q. And then the element entries, we would have these distances. That's the element for UPN. And in front of that, we would have the element for coefficient for UPN minus 1, and then 0, etc. So again, you see how we could build up the stiffness matrix and then have discretized equation in a matrix form. Good. So with this, we all set up. So that means we can now attack the homework. So we have everything discretized. We have the force term discretized, the diffusion term discretized, and also figured out what the boundary conditions will be for the Newman boundary and for the Dirichlet boundary. So now we can actually build up these matrices, stiffness matrix, the unknown vector, and the right-hand side vector F. And then just solve a linear solver for the unknowns D, such that D is now the inverse of the stiffness matrix times F. Good. So that we already know from the finite element approach. You have questions for that part? Is it clear how we would construct these matrices? The stiffness matrix and the right-hand side vector? And then we solve for the unknowns, which are these values of U at the cell centroid points, UP. Good, let me stop sharing this one. So what I will put on the GitHub is the homework, a new homework folder 10 with a Python script and use a template for that. Let me see if I can quickly show you it in the last minute. So it would look something like that. Homework 10, Python script, where we can now set up like the mesh again. And then What we would need, for example, are the centroid positions, which are just the midpoints for each cell. And then we can start basically creating our stiffness matrix and the right-hand side force vector. And so your part will then be to basically construct what are these local contributions from each grid cell, put them into this matrix form, and then solve the matrix form with a linear solver. Right, so I put that into your into the GitHub folder. You can play around with this finite volume implementation, and if you plot it, let me see if I can show you how the figure would kind of look like. So again, it's just the diffusion equation, the steady state, which would, for example, look something like this. The red dots would be the finite volume solution, which we compare against the blue line, the exact solution for that problem. If you want, we had the same example in homework. Was it 7? Let me quickly check. No, it was before that. For the finite element, it was problem set 5, where we had the finite element solution for that same problem. If you want, you can compare it against that one. And here you see the points, the solution is plotted at the cell centroid positions, and the cells are slightly irregular in this case, slightly different sizes. Because that's the main advantage of the finite volume method. It's a very flexible method when it comes to the grid. So a finite difference approach would use a structured grid, same cell sizes everywhere, where here we can play with the cell size, for example. Good. So I put that on GitHub, and then you can play around with it. What I'm planning to look at next Sunday is the wave equation, how we would do the wave equation with the finite volume approach.